Welcome to the colloquium. I'm glad everyone could make it. I'm very happy to introduce Vijay Bhattiprolu, who's a professor in our department and has specifically instructed me not to give any more bio than that, so please get right to it.
Thanks, Sam. Yeah, thanks for having me. So today we'll talk about the inapproximability of sparsest vector in a real subspace. This is joint work with Young Lee, and the following is the optimization problem we care about. So you're given as input a subspace. Oh, I think is the mic on? Yeah, okay, perfect. Given input subspace, V over the reals, and your task is to find the sparsest non-zero vector in the subspace, right? And if you cannot do that, approximate the minimum sparsity. Okay, so we'll develop some notation here. So your task is to find the sparsest non-zero vector in the subspace, where by this notation, I mean the number of non-zero entries in X. Okay? Yeah.
And are you given it as like a basis? You're given a basis or something? Is that?
Yeah, you can assume a basis, kernel, either way. Yeah. The size is polynomial in the dimension, and yeah. Okay. Yeah, and I will, through the course of the talk, refer to this number of non-zero entries as the sparsity of the vector. Okay? Good. Okay, so the following is our main theorem. Unless NP is in BPP, in other words, unless NP admits a randomized polynomial time algorithm. Okay. A mild variation of the P versus NP assumption. For all constants C greater than 1, there exists some function of the dimension such that no polytime algorithm distinguishes on an input subspace V, given an input subspace V, cannot distinguish between following cases. By the way, can the people in the back see if I write this low? Oh, okay. So no lower, no lower. Okay, okay. My remarkable allows me to move stuff up, but I like. But okay. Yeah, let's. Yeah. Is it okay if I raise the problem statement? Is that okay? I kind of want to keep it in one place. Is that okay? Is everyone? Yeah. Okay. Where's the? In the following two cases. Okay, so you can't distinguish between the case where there is a sparse vector in the subspace and the case where all non-zero vectors in the subspace have a lot of sparsity, okay, for any constant c. Okay, so some remarks. So to my knowledge, previous best gap for this problem was something like 1 plus 1 over root n, if your assumption is something like this, p not equal to np, or np doesn't have randomized polynomial time algorithms. Okay? If you assume things like exponential time hypothesis, there might be something much better now. Okay. Okay, and also, previously, versions of this were known over finite fields and over integers. Okay, so the main new contribution is extending the field to the reals. Okay. So let's define these problems. Right, they're very similarly defined. Over FQ, the problem is minimize over X in some subspace. The number of non-zero entries of X. And over the integers, the version usually studied, okay, this is called minimum distance of a chord. That's a common name for this problem. And over the integers, the following problem called the shortest vector problem in an integer lattice is studied. So X belongs to integer span of a set of vectors. X is non-zero. And you will study the minimum length vector that's not zero in an integer lattice. Okay, so this is called the shortest vector problem. Okay, and so both of these problems were known to be hard to approximate within any constant. And for the shortest vector, this was known, I believe, for p at least 1. Okay, so any LP norm that you like, provided it's at least the L1 norm. Okay. But I want to emphasize some other things about this theorem, specifically the proof. Our proof also allows us to assume X is Boolean in the completeness. Okay? In other words, in the S case, not only is there a sparse vector, there's a sparse 0, 1 vector. Okay? Now, as a result of this, as an immediate corollary of this theorem, you get a different proof of the hardness of the shortest vector problem. Okay, this is a foundational problem in lattice-based cryptography, and we get this much simpler proof that, in fact, bypasses the PCP theorem, right? For this problem that, to my knowledge, wasn't known before. Okay? And as a result of this, you also get, sort of, instead of p at least 1, p at least 0 for this. Okay. Okay. Yeah, so let me just write that here. Proof and the reduction. very simple. Don't use the PCP theorem. So if you haven't heard of the PCP theorem, it's a landmark result in the theory of inapproximability. One of the many equivalent ways of stating this theorem is given system Q1 of x equals B1, dot 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 Qm of x equals Bm of local quadratic equations. It is NP hard to distinguish between the following two cases. I use the word yes and no as shorthand for completeness and soundness. Okay. There exists x, let's say in 0, 1 at the n, such that Q1 of x equals B1. Yeah. And no for all x in the hypercube, at least say 0.1 fraction of equations fail. Okay, and what do I mean by this word local? I mean that, so these are a bunch of quadratic equations, and each quadratic involves, say, 10 variables. Okay, a constant number of variables. This is one of the many equivalent ways of stating the PCP theorem. Okay, and by now there are multiple proofs of this theorem, but all of them are quite intricate and technical, and they involve many steps and phases and so on. And so, previously if you wanted to know, hey, what is a hard instance of this problem? What subspaces are hard to find sparse vectors in? What do they look like, right? Or even for this problem, for that matter, that cryptographers care about. You have to, at least if you want to be very theoretically sound, you need to start with the PCP theorem, start with some hard instance of quadratic equations, and then go through all the steps it goes through. And you aren't able to really describe how this looks. It's quite complex, right? But now as a result of this reduction I'll show you, it's almost a random tensor code. That's a hard instance. Almost that, okay? Cool, okay. So final remark. So as is a standard trick in the area, by tensoring, so you take this subspace V and you send it to the t-fold tensor of V, right? If you haven't seen this operation being defined before, I'll define it later in the talk. By this sort of standard trick in the area, you can amplify the gap arbitrarily, right? You can rule out 2 to the log to the 0.99 n approximation, assuming NP is not contained in randomized quasi-poly time. Okay? So this, what I want you to focus on is that this is almost n to the epsilon. Okay, it's not. It's n to the little of 1, but it's almost polynomial in n. Okay, so you can't approximate this problem very well at all, at least in the worst case. Okay? Okay. Great, so I think that's it for the remarks. Now, I just want to give you a quick recap of the reduction paradigm in approximability theory and hardness of approximation before I go to my motivation for studying this. Yeah, good question. So it'll be the kernel of a 0 plus minus 1 entry matrix. Okay? The subspace V. That will be hard at the end.
So, okay, that's like log n bit numbers, or?
You mean of the... So the entries of the matrix will be 1 bit. Yeah, so you need log n bits to store the matrix. So you need n times constant bits to store the matrix, but the bit representation of the vector x, I guess in the S case it's also n bits, right? Yeah. But yeah, if the hard instance were had real numbers as the entries, I think your question is an interesting one, but I mean, we have this very strong structural property for the hard instance. Okay, I think your question is deeper than I'm able to, answer well at the moment, but I think the structure of our hard instance is good for what you might be concerned about. Yeah.
It's related to how is the input represented, right? I think that's...
Yeah. So it's a kernel of a 0 plus minus 1 matrix. Okay. So how are these theorems usually proved in inapproximability? Right? They all go in the following manner. They exhibit what's called a gap-preserving reduction. Okay? Which is a gap-preserving reduction is a poly-time computable map. Okay, in this case, we'll allow randomized polynomial time computable map from an instance IA of an optimization problem A to an instance IB of an optimization problem B, such that, okay, if the value of the instance you started with is large, so it's some constant C1, then the value of the mapped instance is also large. So it's some constant C bar 1. Similarly, the value of the instance is small. Let's use S1. The value of the output instance is small. Okay, and we'll call this gap reducing, gap preserving if the ratio of C bar 1 and S bar 1 is some constant bounded away from 1. It doesn't depend on the size of the instance or anything like that. It doesn't depend on any other parameters, universal constants. Okay. And a typical way of arguing about these reductions, right? This is most of the examples I've seen. Defines two different maps, an encoding map and a decoding map. Okay, that is a map that takes the solution space of this problem A to the solution space of this problem B that we'll call the encoding map. And then another map called the decoding map that takes the solution space of this problem B to the solution space of this problem A. Okay? While also satisfying some assumptions about the values. Right? Okay, so typical proof defines encoding map from from solution x of IA with the value of x being at least C1 to the solution y of IB with value of y being at least C bar 1. Okay? And then the other direction. A decoding map. From solution y with val of y being at least S bar 1 to a solution x with val of x being at least S1. Okay, so the contrapositive of this bottom statement. Okay? It allows us to do existence-based approaches to this for all type statement. Okay? Okay, great. And this is just another little thing I want to mention because there's a lot of convex optimization people in the audience. Like one of the black magic tricks that they do on a daily basis that they don't tell their students is that they don't actually start with the relaxation of a problem, right? They think about the rounding algorithm first, and then they find the relaxation that makes things work, right? This, at least sometimes they do this, and they don't tell their students, right? So similarly here, when you're designing a reduction, it sometimes helps to think of the encoding map first. Like this chicken and egg gets reversed, you think of this thing first, and you use that to guide your reduction, okay? And I think that'll help you a little bit with the intuition today, okay? Okay, all right, so with that, let's quickly go to motivation, and then hopefully I'll show you as much of the proof as possible. That's a good question. Yeah, I'm pretty sure, yeah. In fact, you can guarantee that the entries are, I believe, at least inverse polynomial in D.
So I'm not sure I understand the question. It's for all x. So.
Yeah, but I think what David's asking is consider any x in the subspace V. There are at least CD entries with inverse polynomial magnitude, which is a stronger statement than the sparsity being at least that.
I'm not true. Just divide by a very large number.
Oh, okay, sorry. Yeah, you do have to normalize. So there are at least CD entries with inverse polynomial in the max entry magnitude.
I just worry, yeah, my concern is truncating to a polynomial number of bits and still being able to see this difference.
Yeah. I think it'll work, but I have to think about it. Yeah. Okay. Yeah. Let's even say I don't know until I think about it. But yeah. Okay. All right. So what is my motivation for this? So I gave a previous version of this talk where I focused more on the background and less on the proof. This time I thought I'd experiment with much less of the background, more of the proof. And you guys are all friends, so I figured you'd be okay with me running experiments on you. But so let's blaze through this, hopefully, and then we'll get to the proof. Yeah. So motivation Inapproximability for discrete optimization problems is well developed. But very little is known in the continuous case. Okay, so for continuous optimization problems like the one we're studying today, especially any problem where sparse vectors have good value, sparsity is a good thing. Any such problems is very little known, okay? So that's one of my big motivations. And related to this is that the usual paradigm in discrete inapproximability fails. On this problem and a whole bunch of other cousins and some other problem classes. So this usual paradigm fails, and I'm kind of interested in circumventing this issue. Okay? So what is the usual paradigm? The usual paradigm is start with PCP and apply local gadget reduction. Okay? In other words, you think of local encoding maps. Okay? You start with some vector little x in the original solution space, and you replace each entry of little x by an encoding of that entry. Okay? In some constant dimensional new space. So these are the encoding maps that are typically attempted in this very successful paradigm that gives you hardness of lots of discrete problems. But this paradigm just fails. It fails to kill sparse vectors when we try to show hardness for continuous problems. Okay? What happens is that you have in this, whenever you go for local encoding maps, your decoding map will have to deal with the problem where there are lots of sparse y's that it needs to somehow stitch together to a good solution x of an original discrete problem. And if you have a vector with constantly many non-zero entries and nothing else, it's hard to decode an assignment to some constraint satisfaction problem or discrete optimization problem. Okay, in a nutshell. Okay, so it fails, and it fails for a variety of problems. So sparsest vector problems, polynomial maximization over convex sets, broad class of problems. It fails for graph expansion problems, and so on. Okay. Okay. So the next motivation I have, and actually this is the reason I've cared about it for a long time, is analytic variations of sparsest vector have far-reaching implications in continuous inapproximability. Okay, let me elaborate. Okay, maybe it's time to erase the main theorem. Okay, so in a 2021 work with Wuyong Li and Asaf Naor, we show very, very informally speaking. Okay, I just want to be quick here, so I'm going to be very informal. Assuming the following analytic version of sparsest vector. Okay, this is an analytic proxy for sparsity, for p being less than 2. assuming this is hard, one can get a near characterization of when quadratic maximization over convex sets can be well approximated. Okay, so in other words, we just show that somehow this is the backbone of the issue. Okay, so this is an extremely rich class of continuous optimization problems. They cover several easy tasks, but also several very difficult tasks. And the question is, okay, what are the easy ones and what are the hard ones? And we get some kind of near characterization of this, provided you can show this is hard. And we do this, but we show this is hard by a very controversial complexity hypothesis called the small set expansion hypothesis. Okay? If you can show better hardness of this, assuming, say, the gold standard P not equal to NP, then that same thing ports over to this theorem. Okay, so this is my biggest motivation for studying this.
So if this meta result is assuming that that's hard for any P less than 2?
Yeah. Yeah, you need to get all P less than. So for any fixed P less than 2, it's hard. Okay? And actually, so the ideas that went into the proof of this L0 result already have caused some movement on this. So I think for P equals 1, we have a chance we can do something, but I'm stuck. Okay? Beyond that. Yeah. So as Chaitanya asked, all P is somehow important here. Okay? Okay. Now a couple more examples of this. So there's a cousin of this problem called the 2 to 4 norm. Okay. So if you show this problem is hard, you will get a lot of information about the classical complexity of the quantum separability problem. Don't make me define this, but in a nutshell, it's sort of a problem where you're given a quantum state and you want to test if it's close to separable or not. Okay? And this is a long-standing problem in the quantum information theory, what the classical complexity of this is. So if you could say something strong here, you say something strong there. Okay? And finally, the small set expansion hypothesis itself can be reduced to analytic Sparsest vector of a different type. Okay, so if the subspace V is the top eigenspace of a graph, then the minimum sparsity of a vector epsilon close to the subspace in the L2 distance captures this small set expansion. Okay, so this, long story short, showing hardness of this analytic variation of the problem we're studying today is a necessary intermediate step for the small set expansion conjecture to be true. Okay? All right, so that ends my motivation. With that, you can dive into proof sketches and stuff. How are we doing on time, Sam? Okay. Okay, So before going to the sketch of our proof, I want to show you a warm-up result, specifically finding the sparsest vector in a quadratic manifold. Okay, I can give you a 2-line proof of the hardness of this. This is not due to me. This is an old observation. It is, in fact, the first step in the proof of the PCP theorem. Okay, so let's start with that. And it's a classical example of how you use the distance amplification property of an error-correcting code to generate gap from nothing. Okay, start with no gap, get gap. Okay. So if you take nothing else from my talk, I think this is a clean takeaway. Okay. So I'll quickly define, if you've never seen this, a linear error-correcting code. Is a map, C mapping. Now I'm going to go over the reals, but normally this is defined over finite fields, and everything I say here works if you just replace reals with finite fields. Okay? From a little space to a higher dimensional space, you should think of capital N as being linear and little n. Okay? Such that any two non-equal vectors become very far under the action of this map. Okay? For all x not equal to y in Rn, the L0 distance between x and y, between the encoding of x and the encoding of y is at least d, for some parameter d. Okay? Okay, so in other words, x and y can differ in exactly one entry. Okay, they can differ in as little as exactly one entry, but all of a sudden, after this mapping that blows up number of variables by only a constant, they're far apart in d entries. Okay, and we can actually take this d to be linear and little n and capital N. Okay? So, and in fact, a random matrix say n, I don't know, plus minus 1 to the capital N cross little n allows n equals theta little n equals theta d. Okay? Okay, so these great objects exist, right? And we're going to use this to immediately get gap from nothing. Okay, so our starting point is the following theorem that's equivalent to P not equal to NP. Okay, so, okay, no, I shouldn't call it a theorem. Assumption. So no polynomial time algorithm given a system of quadratic equations can distinguish given a system of quadratic equations the following two cases. There exists a Boolean x satisfying everything. And in the no case, no x satisfies everything. Okay, that is, at least one equation is unsatisfied. Okay, so I'll even assume for all x in Rn. I can do this with a very clever trick, but let's not talk about that. It's tangential to the focus of today. Okay? So in other words, you should think about this as gap 1 versus 1 minus 1 over m. Okay, we're satisfying one fraction of the equations versus 1 minus 1 over number of equations. This is very, very minimal gap. Okay? And now, consider reduction that takes this coding gadget, this error-correcting code, and we define this reduction map, which is, we define the following new system of equations given the system. Okay? Because C is a linear map, you can think of this as a matrix. This is nothing but a new system of quadratic equations. Right? Okay? Yes case, if X satisfies Q1 till Qm, then this vector is equal to this vector. So this vector is equal to this vector. Right? In no case, no matter what X we take, this vector is not equal to this vector, so their encodings must differ in D places. Right? Okay, so we went from 1 minus 1 versus 1 minus 1 over m to 1 versus, say, m over 10. Oh, 1 versus 1 over 10, fraction of the equations. Okay? Assuming we take all these parameters linear in each other. Great, so gap from nothing. Okay, gap producing reduction. So our recipe today is going to be the same. We're going to start from the same assumption that a system of quadratic equations cannot be exactly solved. Okay? This is equivalent to P not equal to NP. Okay? And we are going to use a global coding gadget, this time a tensor code, to produce gap immediately. Okay? I have a lot less time than I expected. So let me eschew telling you the reduction and just give you the high-level sketch and how it connects to related work. Okay, so if you guys remember, I talked about these results over finite fields and over the integers. Okay, so all these guys face the same bottleneck that we face, which is local reductions don't work. So how did they deal with this? This is, over the last few decades, it's become an entire area in its own right. And this paradigm emerged called the homogenization framework. Okay. So in short, the framework goes as follows. You start with, say, quadratic equation hardness. You use the PCP theorem to get local quadratic equations hardness. And then you use locality in a critical way. You do a local gadget reduction to get hardness of an affine variation of our sparsest vector problem. Okay, in other words, minimize over all x. You can replace R by any field, okay, of minimize this. So it's an affine variation of the problem we're studying today. And it turns out this standard paradigm works to show hardness for this problem. Why is that? I'll give you sort of a very dumb observation that'll give you a sense for why. So consider the subspace span of E1, En over 2. Okay? So it's all vectors supported on the first half of the coordinates. Has a ton of sparse vectors in it. Problematic for decoding, right? But if you just shift the subspace with the all ones vector, you have no constant sparsity vectors left. You actually have only vectors with linear sparsity. Okay? However, it's kind of a cheap trick because the points are extremely close to each other. You just shifted them, right? And that causes problems for the homogeneous problem. It hasn't really changed anything. However, for the affine problem, this is enough. Okay? So that's this, kind of cheap trick, but that somehow is a good idea that they do. Okay? And finally, you use a global coding gadget, okay, to show hardness of sparsest vector. Okay. Yeah.
X not equal to 0 in the affine vector.
Uh-huh.
There's no X not equal to 0.
Yeah, you don't need that anymore. Yeah. Because, in particular, X equals 0 doesn't satisfy this condition.
It might have B equal to 0.
Yeah, assuming B is non-zero. If B is 0, then it's a homogeneous. It passes through the origin. It's a subspace, right? Yeah. Okay, good. So now our approach is this. Okay, so we just go directly from this to this. And then the one-liner is that we can simulate a quadratic equation using linear constraints plus a sparsity checker. I think of this L0 notion as a sparsity checker. Okay? Using the combination of these two powers, because this is the problem we're trying to show is hard, you can simulate a quadratic equation by adding linear constraints corresponding to a tensor code. Okay? In other words, so here's what's going on. Let's say you have some quadratic equation. So Q1 inner product XX transpose. This is just another way to write a quadratic equation. Equals P1. Okay? If I had some magical method using linear constraints and sparsity checker to test if a matrix M is rank 1 or not, if I had some magical method to do this, I can just replace this equation by this linear equation. Linear in the entries of M. Okay? And it turns out that symmetric tensor codes have this nice property. That is, if you start with a good code with some additional structure, we needed some additional structure called the overlap property of two code words, and you tensor it, the minimum sparsity code words are rank 1 code words. Any rank 2 matrix in this tensor code has sparsity constant fraction more than the rank 1 code words. Okay, so this is a key step in our approach. Okay? I should mention, so this idea product testing via tensor codes first appeared in a paper of Court and Ostrin. In 2010, I believe. Okay? That idea by itself wasn't enough. And then they actually also go in the same approach, somehow. Okay? We additionally needed to introduce the idea of quotienting. And then this idea appeared in works of Meciancio and Aitai. Say 2012, but also works of Aitai. This idea of not encoding a vector little x by a point in a code, but rather encoding it as a subspace. Okay? So they use this idea to do things over the integers that plays a key role. So we sort of combine these two things, this XX transpose and quotienting in some new way. And that allows us to sort of eschew this approach and just go directly. Okay? I think that's a good place to end.
Are there any questions?
So what was the quotienting thing? You said something, but I could not.
Yeah. Okay, maybe let me just write the reduction, and then you'll see what I mean. Okay, no. I can answer it without going into that. So one kind of beneficial way of comparing what we did with what was done previously is encoding maps. Okay? So code Austrian introduced the idea of going, you want to encode some solution X to quadratic equations by X concatenated with an encoding of X in a code, concatenated with, okay? So they introduced this idea, very nice idea, okay? But it has a problem. Problem is the encoding C of X, it can have sparsity all over the place. All we can say is that it belongs to this interval D comma capital N. So it can fluctuate. Okay? So, but we need this property that encodings preserve value. So it's taking some X that has good value in the sense that it satisfies all the equations, and then it's producing some C of X that has fluctuating value depending on what X we started with. Okay? That's a problem, serious problem. Okay? This problem was handled in older papers, right, of Michiancio. Over the integers. It's a serious problem over the integers and over the reals. It was handled in his papers by the following encoding. Okay, so we go to some higher dimensional space where we have some good code U. And then we divide this U into cosets given by this linear projection T. Okay? And we allow X to be encoded by the entire coset. Now you don't need the entire coset to be sparse, you just need one vector in that coset to be sparse. And that was critical. So now you have this nice property that the L0 norm of this subspace, which is encoding little x, doesn't fluctuate much. And this is key. Okay, and then how we combine all of these things is by just looking at X goes to YY transpose, where Y belongs to the code, and so we just take these two ideas and do some soup, and then that somehow allows several simplifications.
Other questions? Oh.
Yeah, so the problem that you didn't consider, that's right behind you now, the sparsest vector in an affine space. So that problem was very heavily studied, as I'm sure you know, sort of, I don't know, 10, 15 years ago. And at the time, when I was paying attention, the challenge was to come up with an A that would guarantee that that problem would have a unique solution. For some range of parameters, and it was easy to prove that a random matrix A had this property for some range of parameters, but it was very hard to find a particular matrix A.
A unique sparse solution, I assume.
Yeah. A unique sparse solution, exactly, yeah. So, but now, maybe with all these new encoding tricks, there's been progress, or maybe there's some new techniques that might help us find a deterministic A that has a unique encoding.
That's a great idea, and it's a bit of a rabbit hole, my answer to this, and it's vague. I don't see a path immediately, but I should mention to you that Code Austrian's original motivation for their transformation was de-randomization of the proof of minimum distance over code hardness. That was their motivation. And after they did that, Michi Anzio quickly followed up with this paper that takes their reduction, takes the key ideas, and produces a de-randomized coding gadget. So this idea of tensor codes is helpful in explicit constructions of gadgets, but for your question, I like, there's a bit of a distance. I don't immediately see a path, but it's probably related. Yeah. Definitely another idea in the canon to test. Yeah. Mm-hmm.
So I think something, this is on. Okay. So something which is related is like one version of when one want to solve these problems, or you want to do a sparse recovery, which then you have this additional assumption that X is unique there in that completeness case. Or let's say it's a list decoding version, there are few X's. In your reduction, how many X's like in the completeness case, is it the case that there are many X's that are now D-sparse, or also there's a unique?
That's a good question. Yeah. There are in my reduction, there are many X's that are 1 plus epsilon D-sparse.
What about D-sparse exactly? Like,
that could be one, yeah. But it's tricky because in the proof, we sort of use this important freedom. This important property that there are exponentially many vectors in this coset that are sparse, that map down to this little x. It's kind of important that there are exponentially many of them. But of this near minimal sparsity, 1 plus epsilon d. For d, okay, I got to think about it. I don't have an answer off the top of my head. It's a great question. And I suspect that my reduction won't do it. This unique decoding version. That's a great question, yeah.
Looks like there's no more questions, so let's thank Vijay again.